Assalamu alaikum students. Today we shall continue from the NMR spectroscopy, and in today's lecture we have to start from the proton or HNMR spectroscopy. So just like in carbon 13 NMR spectroscopy, we had seen how different types of the peaks were visible on the spectrum of the NMR, and in the same way we will look at the peaks by the hydrogen atoms present in the organic compound to produce some peaks. Again, the concept of the chemical environment will be applied here, which means different chemical environments will influence different types of the protons in the compound, and they will be labeled according to the chemical shift value, which we know is basically expressed in terms of parts per million. The hydrogen NMR spectroscopy uh, can be seen in this case, in this molecule. For example, we have this compound. The name of this compound is pentanthreone. Now, in this compound, we can see the carbonyl group is present at the center. Now, this one is here. Carbonyl group is in the center. Now, you can see there are CH2 groups and CH3 groups on either sides of this carbonyl group. The CH2 is present on the left and the right side of this carbonyl group. And then we have the CH3 and CH3 groups on the extreme ends of this compound. Now, because of asymmetry in this compound, we will see that the hydrogens of the CH2 group will be different as compared to the hydrogens of the CH3. The reason is that these two hydrogen atoms are connected directly with the carbonyl group, and they are connected on the other side with the CH3 group. Same goes over here. The two hydrogen atoms, they are connected directly with the carbonyl group on one side and CH3 group on the other side, which means both of these two groups of CH2, they are chemically in the same environment, and henceforth we will say that all these four hydrogen atoms in combined, they will all produce one peak on the NMR spectrum. We will discuss two types of the peaks here, two types of the spectrum, the low resolution and high resolution. First, we will say about the low resolution NMR spectroscopy of the hydrogen, or you can say low resolution hydrogen NMR spectroscopy of hydrogen 1. Then these four hydrogen atoms of CH2 group, they all produce one single peak. And the same way, the six hydrogen atoms on the other sides will produce one single peak of six hydrogen atoms. They will have one peak, all of these six hydrogen atoms, but they will be in a different chemical shift value. The chemical shift value of these CH2 atoms or hydrogen atoms of the two CH2 group, they are at a different chemical shift value as compared to chemical shift value of the CH3. But you can see here that CH2 is near to the carbonyl group and CH3 are far from the carbonyl group, which means the chemical shift value for the CH2 will be towards a higher chemical shift value. So chemical shift value for the CH2 will be a greater value as compared to the CH3. We have these types of the peaks for the hydrogen NMR, and we will discuss some of the examples to know how they are being produced. And to identify which hydrogen is there in the compound, you have to use the values from the table. So I have already explained all of this thing. You will find this easier to understand by looking at an example. If you look at the molecule methanol, now there is another example, which is methanol. It contains 4 hydrogen atoms. I will draw its structure. Display structure is like this. Now in this case, we have 4 hydrogen atoms in total. Out of these 4 hydrogen atoms, this hydrogen has a different chemical environment as compared to these 3 hydrogen atoms. They are different chemical environment, and this one is in a different environment. So you will find 2 peaks for the hydrogen atoms, 1 peak for all of these 3 hydrogen atoms, and 1 peak for this hydrogen atom. So 2 different molecular environments are present here on the basis of the hydrogen atoms. The energy absorbed by the hydrogen 1 atoms of the CH3 is different from the energy absorbed by the hydrogen 1 atom of the OH. And same trimethylsilane is used, which has 12 hydrogen atoms, and they are all in the same chemical environment, which we have already seen in the previous literature. The solvent that are used in hydrogen NMR are tetrachloromethane, CCl4. It could be CdCl3, which is similar to the CHCl3. Only that we are using the heavier isotope, the deuterium isotope of the hydrogen instead of the hydrogen atom. And this is D2O, similar to the H2O. Again, the heavier isotope of the hydrogen is used here. So these are used in case of the hydrogen NMR spectroscopy, because if we use H1 isotope in these cases, in these solvent, they will produce their own specific peaks in the spectrum, which we do not want. We want the peaks of only the sample which we are using in our experiment. Now, the same table is being provided to identify the location of the peak on the spectrum, and the chemical shift value are based upon the chemical environment. We have these different chemical environments. For example, the hydrogen present in the alkyl, but it is present at the end of the alkyl chain, the chemical shift value is 0.9. Another hydrogen, which is in the middle of the alkyl chain, its chemical shift value 1.4. This hydrogen is present adjacent to the carbonyl, adjacent to the carbon-carbon double bond, or you can say adjacent to the alkene. So it has this value. This hydrogen is adjacent to the carbonyl group, this value. The hydrogen which is adjacent to the arene ring, this C6H5 is basically the arene or benzene ring. So this value. The hydrogen which is next to the oxygen atom, like in alcohols, ethers, and esters. That is not included in your syllabus, ethers. So alcohols and esters, this value. So you can see that as we are moving towards higher, the more electronegative atom, then the chemical shift value is increasing. Now, that's not included. The hydrogen, which is a part of the benzene ring itself, it has this value. All the 6 hydrogen atoms of the benzene ring, they will all have this value of 7.5. The hydrogen which is next to the aldehyde, or the hydrogen which is a part of the aldehyde group, this whole part is the aldehyde group, it has this value. The hydrogen part of hydroxyl group is this value. The part with the phenol, hydrogen of the phenol has this value, and the hydrogen of the carboxylic group has this value. This has a highest value, 11, because it is attached with the most electronegative group. So you will need to use these values. There is another table which you can use to interpret the structure of the compound, and they have located different functional groups at different chemical shift values to identify the compound. You can also you will also need to refer to this table to identify the position of the hydrogen in the compound, and they have labeled all those positions in the compound. It has even the amine compounds, aryl amine, amide compound. So you can use this table. Now we'll look at example of the low resolution NMR spectroscopy. Now in case of the low resolution NMR spectroscopy, you will see only one one peaks of all the hydrogen atoms. You can see here there's one peak here, one peak, and all of these are one peaks. These types of the peaks are only visible in case of the low resolution NMR spectroscopy. And this is also an example of low resolution NMR spectroscopy. These are all the examples of low resolution NMR spectroscopy. But from here onwards, you will find the NMR spectroscopy under high resolution. Now, these are the peaks which are produced under high resolution NMR spectroscopy. Basically, the single peaks are split into more peaks. They are splitting over here. They are not just one. Instead, there are some more of these peaks. For example, here in next page. So you can see that these are just not one single lines. Instead, they are kind of splitting. One single line are split into further peaks. That's the example of the high resolution NMR spectroscopy. So we will differentiate, or you will study in detail about the high resolution NMR spectroscopy and low resolution NMR spectroscopy. First, we will go back to the low resolution NMR spectroscopy, how they are formed and what their applications. So, for example, this is an example. This is a compound of ethanol. Now, this is a display structure of ethanol. Now, you can see that we have three different chemical environments on the basis of the hydrogen atoms. This hydrogen atom is bonded with the oxygen atom. It is got totally different chemical in different environment as compared to the two hydrogen atoms of this CH2 group, and these are in different chemical environment than the three hydrogen atoms of the CH3. Now I have labeled three different chemical environment hydrogen atoms. So these are in different chemical environments. You will see that the peaks are also three, which are indicating three different chemical environments of the hydrogen atoms, but the areas are different. This has the highest area, this one has lower than this one, and this has the least. Now these areas or the peaks are basically indicating how many hydrogen atoms are present in that particular chemical environment. For example, the A peak is representing that it has the highest area, which means it must be indicating these three hydrogen atoms, which I have encircled with black pen. And the peak B must be indicating the blue type of the hydrogen atoms, because they are in quantity of 2. They are in total 2. And the last one, which is C, must be indicating this one single hydrogen atom. And that's also mentioned here. These numbers are indicating the number of hydrogen atoms there. So that was the C peak. The next one was the B peak. And 3 hydrogen atoms were indicating the A peak. So we have basically shown their peaks. Now, what else we need to know? Not just about the peak heights are should be shown, they must also be indicated at which particular chemical shift value they should be present. So the peak at about 1.2 ppm over here, 1.22 ppm, is caused by the hydrogens of the methyl group range, and the range is 0.9 to 1.7 ppm. So I can show this from the table. So 0.9 to 1.7 ppm belongs to the hydrogen of the alkane, or you can say alkyl. Both means the same thing. The next one was a peak at about 3.7 ppm over here. These two are taken, these two spectrum of the same compound taken from different resources. So 3.7 ppm over here and here. They must be present. They must be taken near to the alcohol group. So 0.5 to 6.0. No, this one is hydrogen of the alcohol. Yeah, this one. The hydrogen which is next to the electronegative atom. So alcohol had the oxygen atom present in the molecule. So the hydrogen is present next to the electronegative atom, which has a range of 3.2 to 4.0 ppm. So this does occur in the same range, 3.0 to 4.2 ppm. So this is because of the next to the electronegative atom, and the last one is 5.4 ppm, which is a part of the OH group. So hydrogen, which is a part of the OH group, which must be present from the alcohol. So 0.5 to 6.0. This is the range of the chemical shift, 0.5 to 6.0. So we can see up to 6.0, yes, the range is there. The range, this value does occur in the same range. So we have placed the peaks values according to the chemical shift values and also labeled them according to the number of hydrogen atoms. So that's the spectrum at low resolution. And this TMS, in this spectrum, you can see one large line, but in that case, you see a very small line. So that depends upon the resource book from which they are taken. You must see that the TMS peak or tetramethylsilane peak must be at the value of 0 chemical shift. So I have explained all of these, the whole of this paragraph. Now take another example. This is the example of compound. Okay. Now this compound is basically ethyl methanoate. So ethyl methanoate compound, it has now different chemical environments for the hydrogen atoms. We have different for the methyl group, different for the CH2 group, and different for this methyl group. That's why we have 3 different peak values. Now here, the blue one is present over here. We will need to see exact value from the table, or you need to have a range of this value from the table. The blue peak is closer to the CH3 over here, and the red one that is bonded closer. Now you can also verify which of these two must have the higher chemical shift value, the one which is closer to the electronegative atom or the one which is closer to the carbonyl group. Since it says that red one which is bonded closer to the oxygen must have higher, we can cross check this from the table. So from the table, the hydrogen which is next to the electronegative atom has this value 3.2 to 4.0, and the other one was the next to the carbonyl group. It had 2.2 to 3.0. 2.2 to 3.0 value, and next to electronegative is 4.0. So higher value goes to the 4.0, because in case of ester, the hydrogen was next to the carbonyl group. Up to 3.0. So 4.0 is the one which is for going for the next to the electronegative atom, and the green one can go up to maximum of 3.0 value. So that we have now cross-checked, and these values are indicating their positions according to the chemical environment. So ethyl ethanoate had this type of the NMR spectroscopy, NMR spectrum. Another compound is propanol. Now in propanol, we have one type of environment, another type of second, third, and fourth. We have 4 different types of the chemical environments. Now the one which is a part of the hydroxyl group must be present according to its position. The other, now we have these different chemical environments. This is directly bonded with the OH. This one is far from the OH up to this much distance, and this is in fact at the farthest point from the OH. So that's why we have different chemical environments. And this spectrum belongs to butanol. Why there are 3 peaks for the butanol? For this purpose, I need to draw a structure. Butanol is like this. It has now 3 hydrogen atoms on this carbon, 2 hydrogen atoms on this carbon, and 3 hydrogen atoms on this carbon. Now you can see that we have 3 different chemical environments because these 3 hydrogen atoms are different environment, these 2 are in a different environment because of different groups attached on either sides, and this one is definitely on a different environment. So they are not equivalent. They are all different chemical environments and they are non-equivalent. But these numbers indicate the number of hydrogen atoms. 2 hydrogen atoms are definitely indicating these 2. So 2 hydrogen atoms over here and 3 hydrogen atoms of here and 3 hydrogen atoms of here. But which one must be present on which chemical shift value, that can be checked from the table. And you need to use a table for this purpose. Now, this spectrum belongs to the propane 2-ol. So the structure of propane 2-ol, we have 3 hydrogen atoms of this side, 3 hydrogen atoms of this side, and 1 hydrogen atom over here. In total, we have 1 chemical environment for all of these 6 hydrogen atoms, because you can see that this CH3 bonded with the CH and OH and CH3, and this CH3 is present in the same way with CH, OH, and CH3. That's why these 6 hydrogen atoms are considered to be the part of 1 chemical environment, and this hydrogen atom is in a different environment, and this hydrogen atom is in a different environment. So in total, we would have 3 different chemical environments. One labeled by red, one labeled by black, and one labeled by blue. So you have these 3 peaks. Now you can see 6 is written here, which means they are representing these 2 methyl groups, the hydrogen atoms of these 2 methyl groups. The one is representing this hydrogen, or it could be this one that you need to check from the table by reading the values. So it says the peak at 9.8. No, that's not for this graph. You need to use the values from the table to understand how they are showing different values. But now this compound is of butanol. Butanol is like this. So for this case, I have 1 hydrogen atom over here, 2 hydrogen atoms of here, 2 hydrogen atoms of here, and another 3 hydrogen atoms over here. So in total, we have 4 different environments, 4 different chemical environments. They are non-equivalent, and these are their positions. So it says that the peak at 9.8 ppm, which belongs to this one, is within the aldehyde range. So must be due to the H in the CHO. So this 9.8 is basically for this hydrogen. 9.8 for this hydrogen. The other is at 2.4 ppm, is within the for the hydrogen bonded with the carbon which is next to the carbonyl group. Carbon next to this one, 2.2 ppm. The 2.2 ppm for these 2 hydrogen atoms. Which is joined with the CHO group. Joined to the, for CH2 group, joined to the, so these ones. the ones which are labeled by black, so 2.2 ppm. Then the peak at 1.6 ppm is within the range of HC alkane, so must be due to the two hydrogen atoms in the CH2 group not directly joined to the CH2 group. So 1.6 ppm is for these two hydrogen atoms, and at the last, the 1 ppm, so must be due to the three hydrogen atoms in the CH3 group. So 1 ppm, 1.0. So they are now labeled over here. On the basis of the hydrogen atoms and on the basis of the chemical shift value, we have indicated which hydrogen atoms are present at which positions. And they are their different heights. Now, the other type of the NMR spectroscopy is high resolution NMR spectroscopy. Now, there's a different concept which is now applied here. We have the splitting pattern. Splitting pattern means that within the structure of the organic compounds, the hydrogen atoms of adjacent carbon atom, the hydrogens of the adjacent, let's suppose if I have two carbon atoms and they both are bonded with the hydrogen atoms, let's suppose this one is bonded with the hydrogen atom and the other one is also bonded with the hydrogen atom. Now, what we have here, the hydrogen atoms of the one carbon atom will be influencing the hydrogen atoms of the other carbon. To make it simple, you have two carbons and both carbons are bonded with the hydrogens. This hydrogen will have influence of this hydrogen and this hydrogen will have an influence of the on the red hydrogen. These are the hydrogens which are present on the adjacent. You can see that adjacent means the carbons which are bonded next to each other. So these are called adjacent carbon atoms. These hydrogens will create splitting of their peaks. If I say that let's suppose if I had two hydrogen atoms on this carbon, on the blue carbon, I have two hydrogen atoms. So I will put a peak for blue one and one peak for the red one. On the basis of different chemical environments, I will need to put two peaks. But this hydrogen will now create its own magnetic field effect on the blue hydrogen atoms. The red hydrogen atom is creating effect on the blue hydrogen atoms. And as a result of this, they will be splitting according to the formula of n plus 1. N plus 1 means n indicates the number of hydrogen atoms. N is number of the adjacent hydrogen atoms. For creating splitting on the blue one, the n is the number of hydrogen atoms. Here it is only one. There's just one carbon atom. So putting the value here, you will have 1 plus 1 giving 2. So the number of hydrogen atoms which are producing the effect of splitting will be counted here. So this one hydrogen atoms will become 1 plus 1 equal to 2. So this blue line will no longer remain one single line. Instead, this will convert into two peaks like this. You can either indicate in the form of the triangles or you can also indicate in the form of the vertical lines. So this one single line is converted into two lines. Now, if I want to study the effect of the blue hydrogen atoms on the red hydrogen atom, then I will say that the number of hydrogen atoms which are producing the effect are in total 2. So putting the value in the same formula, which is n plus 1. So n plus 1 will have 2 over here. because the number of adjacent hydrogen atoms are now 2. So I will have 2 plus 1 is equal to 3. So the red peak will now split into 3 lines. The 3 lines must be in the symmetrical way. So it will be like this. Like this. I have now 3 peaks of this one straight line. This splitting is observed in case of the high resolution NMR spectroscopy. We are looking at a high resolution how the hydrogen atoms are basically affecting the peaks of the adjacent carbon atoms. So this can only be observed in case of the adjacent carbon atoms by following this rule. Now these are the peaks here. When there is just one single peak, even after considering the high resolution NMR spectroscopy, and you just find only one peak, that will be called as singlet. However, if a peak is divided into two which is split into 2 peaks, that will be called as doublet. If a peak is split into 3 peaks, it is called triplet, indicated like this. You can see one peak is as like one peak. 2 peaks are indicated by 2 equal magnitudes. 3 peaks are indicated in such a way that the sideways peaks are smaller and the center one is higher. And the 3 peaks, the 4 peaks are indicated like this. You can see the extreme peaks are of same magnitude and the central 2 peaks are of the same magnitude and they are of the higher value. So that's how you will need to indicate, or you need to understand how the splitting occurs. So this splitting is definitely caused by, I can take example for this type of the peak in which there were 2 carbon atoms. On one carbon atom, it had 3 hydrogen atoms. And on the other carbon atom, it had only 1 hydrogen. Now, these 4 peaks are of this single hydrogen, which were caused by the 3 hydrogen atoms. The 3 hydrogen atoms were playing their role of splitting on the peak of the hydrogen labeled blue. So these 4 peaks are because of these 3, because you need to apply the formula n plus 1, which means 3 plus 1 giving 4. So 4 are produced by these 3 hydrogen atoms of the adjacent carbon. Now we will also study them in detail by taking some examples. And these are the ratios. These ratios are basically the ratios of the intensities. For example, if there are two peaks or there is a doublet, then the ratio will be the same. So 1:1 must be shown here. This is 1:1. If there are triplet here, then the ratio is 1:2:1. If there are 4 lines, then they are represented as 1:3:3:1. And there's still one more addition in which we have 1:4:6:4:1, which will be giving 5 peaks. So this splitting is caused by the spin-spin coupling. You will have this spin-spin coupling, which will result in the splitting of the peaks, spin-spin coupling. But some rules must be followed here. The protons in identical chemical environments do not split each other's peaks. So those which are present in the same environment, they will not be splitted. Let's suppose if I take an example of CH3 bonded with CH3, they are the same. They are in the same chemical environment. They will produce one single peak. They cannot cause splitting of the peaks. So they will be the same. They will produce only one single peak. The peak of a proton adjacent to n protons in a different environment is split into n plus 1 lines. That's what we have followed. This rule must be followed here. The relative intensity of the n plus lines are in the pattern shown. The interaction between protons separated by more than 3 bonds is usually too weak to cause any splitting of each other's peaks. So if we have a distance of more than 3, then you cannot find splitting. The example which I have been including is those in which we have a distance of minimum 3. Let's suppose if I have 2 carbon atoms, this one has 1 hydrogen atom and this one has its own hydrogen atom, and there are, let's suppose, 2 hydrogen atoms on this carbon. You can also take their distance in terms of bond distance. Bond distance means you need to count how much distance is covered by the bonds. If I want to move from the red hydrogen atom to the blue hydrogen atom, then I will count like this: 1, 2, and 3. One bond distance, the second bond distance, and the third bond distance. So a minimum of 3 bond distance is required for creating splitting on the neighboring hydrogen atoms or hydrogen of the adjacent carbon. But if the hydrogen is present, in fact, at a farther away, let's suppose if somehow there was no hydrogen atom on this carbon and there was used to be another carbon over here on which hydrogen was bonded, then this red hydrogen atom could not affect the black one, because in this case the distance would be higher: 2, 3, and 4. 4 bond distance. The 4 bond distance cannot be affected. Now let's take an example. We have this example in which we have 3 hydrogen atoms over here, and this one is CHO. Now these 3 hydrogen atoms will create an effect on this one single hydrogen atom, and this one single hydrogen atom will have effect on these 3 hydrogen atoms. The peak, because of this hydrogen on these 3, will be doublet. The doublet peak will be observed for these 3 hydrogen atoms, because by applying n plus 1 rule, there is one hydrogen atom, so n plus 1 will give you 2. So a doublet will be seen for these 3 hydrogen atoms, and then for the 3 hydrogen atoms of yellow color affecting the purple one will create a quartet in which we had peaks like this for the red for the purple hydrogen atom, because n plus 1 gives 4. So this will be indicating this hydrogen atom. Now here's an example of the compound. In this case, you can see there are 3 carbon atoms. The central carbon atom is bonded with the 3 CH3 groups, with the 2 CH3 groups. Now, the hydrogen atoms of the central one, they are in different environment than these hydrogen atoms, and the side ones are in the same environment. The hydrogen atoms on the either CH3 groups, they are in the same environment because they both are connected with the same CH2 group. Now, the peak by the central hydrogen atoms on the either sides will be triplet, because you can see that the hydrogen atoms which are creating the effect, they are in total 2. So n plus 1 will give you 3. So triplet will be seen by for the purple ones. Now let's take the example of the 112 trichloroethane. 112 trichloroethane. Now here in this case, you have 2 hydrogen atoms in total. One hydrogen atom labeled red and the other hydrogen atom labeled blue. Now for this case, this hydrogen will create effect on this hydrogen, and this hydrogen will create effect on this hydrogen atom, which means you will have two types of the peaks here, and the peaks will both be doublet. Both of the peaks will be doublet in this case. No, the blue ones are in total 2. So 2 blue atoms over here and 1 red atom, which means the peak of the red one will now be split into 3. So 3 peaks are seen over here. The hydrogen atom over here is split into 3 peaks. You can see, if you could clearly see from here. So the red hydrogen atom is split into 3 peaks because these two will create effect of triplet, and the red one, if it creating effect on the blue hydrogen atoms, then it will convert it into the doublet. So doublet is seen in the blue hydrogen atom labeled by this dotted blue circle, and the red hydrogen atom is indicated by the stripped red circle. Now take another example. This is an example of the ethanol. Now in case of ethanol, we have 3 different chemical environments. One for this hydrogen, two for another for these 2 hydrogen atoms, and another for these 3 hydrogen atoms. So on the basis of the chemical environment, we have placed them on the chemical shift values. Now we also need to apply the high resolution NMR on the basis of which we'll split the lines. So there's a rule here which I need to add here, that if the carbon is bonded with a highly electronegative atom, let's suppose like oxygen or nitrogen or chlorine or fluorine, if the carbon is bonded with an electronegative atom, then that electronegative atom ha- cannot let the hydrogens to create effect of splitting, which means this hydrogen atom will not be able to cause splitting on the other hydrogen atoms, which means that this hydrogen atom will remain in its own way. It will be present in the form of the singlet. So this singlet over here is because of the OH hydrogen. This OH hydrogen is present over here in the form of singlet. Now it is not affected by these hydrogen atoms, and this hydrogen atom will not affect these hydrogen atoms, which means these two will now create an interaction on each other. So if there are 3 hydrogen atoms and they are producing the effect on the red one, they will convert these red one into quartet. So quartet peak can be seen over here. The B peak, they are basically of the CH2. The CH2 part is shown over here, and these 3 hydrogen atoms are split into uh, are split into triplet because of these 2 hydrogen atoms. The 3 hydrogen atom will be split into triplet because of 2 hydrogen atom, and you can see the split triplet over here. So 3 hydrogen atoms of the CH3 are shown over here. So that's how we have now identified that this is the NMR spectrum of the ethanol. And this is another spectrum taken from another source book, which indicates the hydrogen atoms on with the number over here: 1 hydrogen atom, 2 hydrogen atom, and 3 hydrogen atoms, like this one. So 3 hydrogen atom means CH3, 2 hydrogen atoms means CH2, the part is CH2 over here, and 1 hydrogen atom means that was part of the OH group. Now take another example. This is the example of the ester ethyl methanoate. So we have 3 different chemical environments. Now these 3 hydrogen atoms, they will not be split because in fact there is a large distance between the hydrogen atoms, more than 3 bond distance. So these green lines, these green hydrogen atoms are indicated by one single peak of 3 hydrogen atoms. So this is B. The red one must be influenced by these 3 hydrogen atoms. So 3 means n plus 1 will give you 4 over here. So the red ones must be converted into quartet, and the blue ones must be converted by the hydrogen atoms, and they will produce n plus 1 is equal to 3. So the blue ones are converted into triplet. So we have triplet over here, quartet over here, and singlet for this hydrogen atom. Now at which chemical shift values are they present? That must be referred from the table. And this is also the same. Now this one is a ketone. So in case of ketone, these three hydrogen atoms, they will not be affected because uh, they are hindered by the presence of the carbonyl group, which will increase the distance, and in fact which is a electron withdrawing group. Both the factors are basically preventing or isolating the CH3 group on one side. It will be indicated as a singlet. So singlet over here, and the B hydrogen atoms, they are converted into quartet because of these three hydrogen atoms, and the hydrogen atoms indicated by C are converted into triplet because of the two hydrogen atoms. Now another example, which is methyl propanoate. So same, which we already discussed. This is the same example. Ethyl ethanoate. Now ethyl ethanoate have chemical environments of three different types, and same triplet can be seen over here. A quartet can be seen over here. This is quartet of the two hydrogen atoms. The two hydrogen atoms, these two hydrogen atoms are indicated by 2 over here, which will convert it into triplet, quartet, because of the three hydrogen atoms of the methyl group. And the three hydrogen atoms of the methyl be converted into triplet because of the CH2 group. The same word symbols, the integration signs are indicated here, or you can say the trace indicates the number of the hydrogen atoms. So that was all about the splitting of the hydrogen atoms. One thing which is now left for the benzene compounds. In case of the benzene compound, then all of the hydrogen atoms are indicated by one peak. If we have this compound, then all of the hydrogen atoms of this benzene will be indicated by one single peak. Whereas now the other hydrogen atom, we have to indicate which isomer is producing this spectrum. So you can see that there are 4 different environments. So over here, if you look at here, you will see 4 different chemical environments. All the hydrogen atoms of one peak, and then one peak for these two hydrogen atoms, one peak for these two hydrogen atoms because they are in different environment, and one peak for this hydrogen atom. So singlet will be seen for this, triplet for this, triplet for this, and singlet for this. So there should be 2 singlets. So singlet over here, singlet over here, and there are 2 triplets because both CH2s are creating the splitting in both of them, causing the spin-spin coupling. So spin-spin coupling because of 2 CH2 groups. So this spectrum must be because of this isomer number 1, which is now discussed in detail over here. And if you look for this compound, then there are 1, 2, 3, 4, 5 different chemical environments, and there are in total 2 singlets, one singlet over here and one singlet over here. This 3CH3, this singlet is because of 3 hydrogen. It could be of this one, or it could be of this one, and another singlet over here. Now you can see one singlet present over here, which is this one. So one singlet represented by the blue hydrogen atoms. Now I have to show duplet of 2H, duplet of the 2H. So duplet of the 2H can be seen here. These 2 hydrogen atoms, they are in the same environment, and then another 2H. I'm not telling which chemical shift is belonging to which one. You need to use the table. So these 2 are in the same environment. So these are all done. Now one singlet must be indicated by the hydrogen atoms of the whole benzene ring. So one goes to the benzene ring that is mentioned over here. So that's how this compound, the aspirin compound, must be this one. There's a difference here. Yeah, there's a kind of difference. This is not a compound. This one is, because paracetamol has one hydrogen over here which is prevented from the other hydrogen atom. So this one will give you singlet. So this is from this hydrogen atom, and then you have two hydrogen atoms with the doublets. So these are in the same environment because they are at the same distance from the other groups. And then we have two hydrogen atoms and they are in the same environment because they are present at the same distance from the other groups. And at the last, we have one singlet of this hydrogen. So one singlet for this hydrogen. That's how we have now indicated that this compound belongs to, paracetamol belongs to this spectrum. Now at the end, we have the use of deuterium. Basically, deuterium is not being expressed or not being indicated by the NMR spectroscopy. They are hidden. Only the hydrogen 1 spectrum can be seen. Now using the deuterium, we can make solvent of water, which is called D2O. Now this D2O, when dissolved with ethanol, it will exchange the hydrogen of the OH part and convert into the DO. Now this means that the peak of the OH, which was previously shown over here, is now invisible over here. It was visible, this OH peak was visible here, but it is now invisible over here. Which we can say that the peak of the OH is now, OH peak is now missing. The OH peak is now missing. And that missing of the peak will help you to identify whether the compound is alcohol type or it could be amine. In fact, you can also have the same phenomena in case of the amine compounds, NH2 bonded with the alkyl groups. So the same case of the same case of the splitting will be here. The same case of the exchange will be here. The same case of the exchange will be here. You can see from the reaction type over here. This is alcohol, which is now dissolved in the water. It will produce ethanol and water again. But if we dissolve it in the D2O, if we dissolve it in the D2O, then this will now be indicated like this. So when alcohol group is present in the water, this OH is now converted into OD. Now that OD is present in the alcohol, and the water is now converted into HOD. This is hydrogen and this is deuterium. This is still of water. This is water. This formula is of water, but the D part is now replaced over here. And if we have the amide compound, then this hydrogen of the amide will be exchanged with the deuterium. So you will now have ND over here along with the carbonyl group, and the water is converted into HOD. You know that water could be H2O, it could be D2O, but what if we have one hydrogen atom and one deuterium, then you will write it like this, HOD. So basically, the exchange of the hydrogens with the deuterium will help you to indicate the presence of the OH or the NH peak. For example, over here, we had the compound of ethanol. Ethanol, when it was present in the absence of the D2O and when it was in the presence of the D2O. If there was no D2O, then you had the peak of the OH labeled over here. This peak you can see on this chemical shift value. But if you put the alcohol in the D2O, then there will be exchange of the hydrogen by the deuterium, and the peak will not be visible in the spectrum. So you do not see any peak over here. It is now empty. It is now invisible, which indicate that there is now a missing of one peak of the OH part, and that will help you to identify whether the compound is ethanol or any alcohol, or it could be amine compound, or it could be amide. So there are three different compounds which you can find out using the D2O, the alcohol, the amine, and the amide. Three different chemical compounds. So amines over here rhylamines, amides, and the alcohols. And in fact, the carboxylic acid, because this one has also OH part. Phenol has OH part, alcohol has OH part. So these three all belongs to OH, and these three belongs to the NH2 or NH. So these can be indicated by using the D2O. Deuterium oxide is used to help us identifying the missing pink of the OH or the amine. So that was all about the A2 chemistry. We have now officially completed the syllabus of the A2. So from onwards, we will discuss some trickiest and challenging questions of the past papers, and do let me know if you have any questions. Okay, students, take care and Allah Hafiz, everyone.